And welcome, ladies and gentlemen, to another exciting episode of PASCO Live. We're here in PASCO Laboratories. I'm joined by Heidi Brennan. Hi, Heidi.
Hey, how
nice
are
to
you?
have you here. And I'm JP. And Heidi, a lot of people ask me a question. What do they ask me?
What does the P stand for?
What does the P stand for? You're going to be surprised to know that the P actually stands for predictive. Now, I know that's a funny middle name, and you'd have to blame my parents, but it really applies here because today's topic is looking at computational modeling. That's right, computational modeling. And computational modeling allows us to make some predictive calculations, make some predictions, and it also allows us to take a look at sometimes the real versus the ideal. Now, if you're wondering, like, what is this computational modeling? What are you talking about? You're actually seeing computational modeling often. Heidi and I are from Florida, and we're
Don't hold it against us.
Yeah. But Tampa, with Tampa Bay coming up, I know everybody's watching the big game, but we also watch hurricanes, and hurricanes are extremely chaotic. There's a tremendous amount of data that we get. We fly in airplanes, we get pressure, we get locations, we get all of this, and we dump it all into a computer program that generates a model. And that model might look like something that you see here on the screen. Now, this is a very common predictive model. Heidi and I see this all the time. You notice that there's a cone that they say, like a cone of certainty where that hurricane may land. You're familiar with that, right?
Cone of uncertainty.
And why is there a cone? Why is it not just a line that says this is where the hurricane's going to go?
Because a lot of things can happen
A lot of things can happen. That's right. And there's more than one model. In fact, if you look real close at the different types of models for a hurricane, you'll find out there are multiple models. Some of them veer a little bit to the left, some of them veer a little bit to the right, and you get this cone that says roughly, if we look at all of these computational models, the hurricane may go somewhere in this area, roughly. And that's just one example of how computational modeling really kind of helps us take vast amounts of data and turn it into something very usable. We also know that if you're trying to get to Mars, like I'm hoping to do someday, you're going to use a model to help us leave Earth and get to Mars. Now, we haven't done it enough that we have a roadmap to get there, so we have to use computational modeling. We figure out with all the data, things about the location of planets, orbits, gravitational pulls from the planets and their alignment, dump it into a program, and bang, here you have it. A computational model that says this is how you get to Mars. We also do that in sports quite a bit. Here's an example of computational modeling for soccer and taking a look at if I'm playing against this team based on all the things that they've done in the past, what are the best chances they're going to be passing in a certain area? Well, I have a model for that, and it allows me to actually play better soccer, or, for those of you in Tampa, better football. The point is that we use computational modeling a lot, and those of you who are in chemistry or teach chemistry recognize that models take all types of shapes and forms, like this model, for example, PV equals nRT. What do we call that?
PV equals
nRT. Yeah, what do we call that?
gas law?
We do. We call it the gas law, but we call it the ideal gas law. Good, Heidi, right. Yeah, you got it.
K8 here, I apologize.
It's the ideal gas law. The ideal gas law. And why do we call it the ideal gas law? Because it's not real. It's not real because it's just a model of how gases behave. So you're probably wondering then, how do I take this computational modeling idea, this predictive capability to look at the real versus the ideal and bring it into the classroom? You can't bring a hurricane into your classroom. We can't get to Mars, but we can bring computational modeling right to your classroom, and Heidi's going to start off showing us how.
Yeah, I want to start off with a middle school example because I think
Awesome.
it's a great way to introduce it to students. And I'm going to be using our Codenode Cart, and our light spring for this demonstration. And I've made just a simple ramp here with one book to start to give me my height, and then a book at the end because we're going to be looking at force on impact.
So you're using this little device here. It's got our code node. The code node is actually clipped in here, so it's the code node device that that goes very nicely into the cart, and it goes really nicely into the cart like that. And now I'm actually ready to do some experimentation.
Right. So students need to start diving into Newton's second law. So what's interesting about this is you can do cart position and cart velocity, but we can't measure force with the cart on its own.
This device does not measure force.
No, it doesn't.
But I want to know force.
Yeah, so what other two pieces do I need?
Well, Newton tells me that if I want to know force, I need to know mass and I need to know acceleration.
Perfect. Now this can measure acceleration, and I can get the mass of this vehicle, which is 0.157 kilograms.
0.157.
Yeah,
I'll watch
so,
for that number.
So
okay.
let's take it into Blockly, and Blockly is our coding software that's embedded within both Capstone and SparkView, and I'm going to use SparkView for the example today.
Okay.
And this is the challenge to students. All right, so we can't measure force with a cart, but I can get those other two data points where I can create a function, a mathematical function in my coding program that will give me force on impact when it hits here.
So just to be clear, we're creating a computational model that's going to predict the force. It's a predictive model, and it's predicting force. It is looking at data that's coming, like we said, vast amounts of data, dumped into a computational model that's going to give me a predictive force on impact.
Yeah, so let me walk them through real quick what I created here. And you can actually access this activity in our experiment library from PASCO.com. It's called Computational Modeling Force on Impact. All right, so I've created three variables here: mass, because I have to plug in the mass of the vehicle. I've set current force to 0 and max force to 0. Those are two really important parts here, because my current force will be set at that mathematical equation that I need. So
after it does the calculation.
Yeah, so it's going to take the max force when it hits that, multiplied by 0.157 kilograms.
Which is the mass that we measured earlier.
So this is the part that might look a little confusing. It's saying if the current force is greater than max force. I have max force set at 0. So as soon as it hits the current force, it'll swap those out. It'll set max force to current.
And it drops that correct number into the equation now. It allows me to do that calculation. Your program is just set up to do F equals MA. It's doing the calculation based on the real-time data that's being brought into the model.
Terrific. So here I've created a screen because I do have a numerical output, which is going to be force. And it's important in the activity for the students to measure that max acceleration as well, so they can go back and look at their math and see if the prediction was correct.
Great.
All right, so ideally they would do this 5 times, but I'm going to do just 2 runs to kind of give you the feel on how this works. I have it set up. This is 5.5 centimeters for the first height. I'm going to start my program. Excellent. So
awesome. Okay, so we see a very nice measurement of acceleration on the y-axis. I see I have a maximum acceleration. This device was able to calculate that. It didn't give me the force because it doesn't measure force, but I do have a force number.
Yes, you certainly do, because we built that into the computational model.
The computational model calculates predictive the force. And so I see 2.35
newtons.
All
right, so let's increase the height here. So I'm going to go up to 11 centimeters. And since I've increased my height, what 2 factors should also increase?
Well, if F equals ma, the mass isn't going to change.
Correct.
But the acceleration probably will. I'm going down a much steeper ramp.
Yep.
If acceleration goes up, I'm going to guess force goes up.
All right, let's see. Set it up again. Start the program. Excellent. So I saw exactly what I would have predicted to see.
We have a new maximum acceleration, and that's the number that's being used in the calculation to give me the new force.
All right, so I increased up to 3.93
Oh,
newtons.
good. So I'm able to compare the two. I see that there's been a massive increase, and the force increased. And so what would I do with my students now?
Yeah, so they're going to take it a step further, and they're going to calculate their average for their 5 runs for height 1 and height 2 for acceleration and for force as well. And then they're going to take those numbers and they're going to calculate the increase of acceleration from height 1 to 2 and the increase in force from height 1 to height 2. And if they've done this correctly and their program is correct, you're going to see the increase in percentage for acceleration and force will almost be exactly equal.
And so what the students will have done at that point they will determine the relationship of F equal ma. They rediscovered Newton's second law through a computational model. That is a great activity, and it is in the library, and you're able to access it right now. If you go onto the video, into the
into the experiment library.
The experiment library, and you're able to get this and do it and work it with your students. I think you'll get really interesting results. But then you might be wondering, how can I take this a step further? Now, Heidi just showed us that I can bring this into my middle school classroom. I can calculate force based on acceleration and based on mass and F equals ma, and that's a great standard at the middle school level. But how do I bring this up a little bit higher? How can I actually set the model up to look at what's predicted versus what really happens? And to look at that, we're going to bring in JJ Planck. Hi, JJ.
Hey, JP.
Nice to have you here.
Thank you.
Always a pleasure to have you here. And so what JJ is going to show us is that very complicated world of physics that oftentimes gets us a little bit confused. We start thinking about simple calculations. Like I want to calculate velocity, but then if I start thinking about things like air drag and gravity and the wind blowing in the room, and then my numbers never quite line up correctly, do they?
Yeah, that's right. And so in physics, a lot of times what we do is we simplify things to help, make the ability to understand the concept easier, and then use it, extend it to different topics. But one of those simplifications that we make all the time, especially in the world of AP, is ignore air resistance, ignore friction.
Right. Ignore friction.
Right.
And that's the same problem we have. We call it the ideal gas law, but I'm beginning to think in physics we should call them all ideal velocity laws, ideal momentum laws, because they're ignoring really some very important stuff.
Yeah, and so with a projectile, as it flies through the air, we can relatively easily determine equations for the position in the y and the x, depending on how much time it's been in the air. We can do this sort of a division of the equations of motion in x and y and figure that out. And we can plot that if we wanted to. But as soon as you throw in air resistance or air drag, things grow in complexity.
Sure. It doesn't do what it's supposed to do mathematically, does it?
Yeah, it does not. And so
put this in presentation.
Right? Good. Thank you very much.
And we'll show this to our audience at home.
Perfect. Is it through? Okay, perfect. So this is actually part of a presentation that Dan and I did for the AAPT, American Association of Physics Teachers, summer meeting this last summer. So these slides have been prepared ahead of time. And they're saved for you, and I'll show you a link at the end so you can access this as well as the files that I'm going to open in just a second.
That's nice of you to give to them.
Oh, thank you. And so these two equations here are complicated. They look complicated, right? They've got this calculus built into them. And you see there's that m d squared x dt squared on one side, and then there's some other dx just a bunch of, there's a mess, calculus mess here. And
calculus, right, which is essentially trying to tell me got to measure small amounts of x and got to measure small amounts of y, and I got to continually do those small amounts of measurements, which is what calculus is great for, to get a real answer.
Yeah.
Which is nothing anybody wants to do.
That's right. Yeah.
That is awful.
Yeah. And so what happens is when you introduce air drag and projectile motion, the force from the air drag changes depending on how fast the projectile is going, and x and y, right? So we can still divide those. But when you do that, you've got equations that have acceleration, right? Ma, F equals ma, do the second law. We're talking about forces. You got an acceleration, and now you've got this velocity term that's in there. And when you do that, you end up with a differential equation. And then you're just going to start scrambling brains.
And you'll have your kids dropping out of class.
Right,
because
exactly.
It's now already beyond complicated. Thank goodness for computational modeling.
Yeah, and so computational modeling gives us the ability to take that expression, those complex expressions, and actually break them down. And instead of actually solving them in terms of the calculus, we do exactly what you said, tiny little time steps, like miniature calculations one at a time.
That the calculator doesn't mind doing.
That's right. The calculator in the computer is much more powerful, and it can, or the processor is much more powerful, and it can handle it. And so what we do is we use this momentum particle model. And so the momentum particle model is the formal expression for it. But what you do is you have a particle that's moving, and if you know the forces that are acting on it at any time, right, then you can figure out what the impulse is that's being imparted to that particle. If you know the impulse, then you know that's change in momentum. If you know change in momentum, then you know change in velocity. If you know change in velocity, you know change in position. And this is all assuming a tiny little time step for all that. That's sort of
change one little thing here, and it carries it all the way through the calculation to the end.
And that's exactly what this is. And this is looks fairly complicated, but it says there in basic principle exactly what's happening. But those expressions there are exactly what we're going to program into Capstone or into our Blockly code. And so I have here, zoomed in too far, projectile.
So we've got Capstone opened, and we're going to swap that screen. So
Look at this.
So our folks at home can see that.
Perfect.
Very good. Okay. So at home, our folks are looking at Capstone, which is our other software program, the more advanced program, but it also has Blockly embedded, so we can do computational modeling. We can do programming right within the software.
That's right. And so what we have here is this, in this set of code, well, let me just start from the top. At the top are a bunch of variables. We're going to define them. Drag coefficient, initial speed, initial angle, position in the x, where it's starting in the x, where it's starting in the y, what the mass of the projectile is, what gravity is. We can change that if we want to pretend like we're on Mars or whatever.
Nice.
And then our time step, that's what dt is. And we're going to set time equal to 0. And then we use those definitions and we run it through this code here. And all this code does essentially is take the sum of the forces in the x and the y and then use those to do exactly what we said. And so here's a line, a block for the drag force in the x direction.
I see. So now we're able to introduce variables beyond our standard calculation.
That's right.
We're able to introduce some of the real.
That's right. And so here's the drag force in the y. And then this expression right here just sums them up. So this is the total forces in the x direction. And in this case, the only force in the x direction, as we should know as a projectile, the gravity only acts vertically. The only force is from air drag. And so that's why it says force x is air drag.
Yep.
And but force y has a combination of mg plus that drag force in the y direction. And now, if, like I said, if we know the force, we know the impulse, we know the change in momentum, that's exactly what this line does.
And adding yet another calculation to make it more real.
Yes, and so there's momentum. If we know change in momentum, we know change in velocity. You just divide by the mass, right? That gives you the velocity. And if we know the change in velocity, then we know the change in position in x and y. And so we have now created code that goes in these tiny little time steps and calculates a new position every loop.
And done very rapidly with the speed of the processor, so that what I'm getting is an actual calculation that's giving me some interesting results. And so then what I see here then is that prediction.
Yeah, so let's do this. I'm going to go in here and I'm going to turn off air drag for a second. We'll make the coefficient equal to 0. So this essentially means there's no air drag. And so we're going to generate this ideal set of data. And so here's our projectile flying through the air with no air drag. And like I said, we could have had our students very easily use kinematics to figure out what this graph or what this data should look like, right? But as soon as we add air drag, it gets complex. And let me show you exactly what that looks like. If I go in here and now I give my air drag coefficient, let's make it something big. We'll just call it 2. And we run this code again. Whoops. Delete that. That was too much air drag.
It fell right to the ground.
Yeah. Let's do 1. Again, too much air drag. Let's do 0.5 instead. Or actually, let's do 0.1. Let's see what this does.
And that seems like a more realistic number.
Yeah.
So
here is...
Holy cow.
Yeah.
So no wonder 2. Look at that.
Yeah.
So
Let's-
even at 0.1,
that's
not air drag. You're doing this in water.
Exactly. Let's do 0.01.
Okay. Let's look at that.
Okay. So now the projectile is experiencing air drag.
This is a little bit more like what I would expect. So the green line is really very ideal. It didn't take into account air drag. You dropped air drag in. It's doing the calculations. Now it's displaying the model. So I actually see that with air drag, it's going to be a different projectile.
That's right. And so in terms of an application for something like this, the way that this gets used, that I suggest this gets used, is use it as a practicum for your students. They're going to learn about projectile motion. If you want to do and include this computational modeling format, they can use that data. They can literally go to, they can literally go to that data and figure out where the height of the projectile is going to be at some range. And then you can have them set targets up.
To predict that, to see if that's real.
Exactly.
Based on the actual data. So now they can compare the real event based on the data that they've supplied, and now it really is becoming the real versus the ideal.
That's exactly right. And so they can, in this picture that you see here on this slide has a metal projectile, and so the drag coefficient is the same as a projectile with the same shape, but it has a really high mass, so that drag coefficient doesn't really play a big role. But if you use a little Nerf ball that's about the same size,
oh, the drag would have a huge influence.
then you're going to have a huge influence. And so it's a nice challenge for your students to try to see if they can, do that.
Nice.
And so here is a link to a video. So when you get this PowerPoint,
so if you're not catching all of this right now, JJ has already done this and explained it in even greater detail on a live performance during a PASCO live Physics Day.
Yeah, Day of
and
Physics.
That link that you're providing there will actually take you to that, and you can watch where he does the actual launching of the projectile and shows, here's the real, here's the ideal, let's see how close they came, and now do I need to adjust my parameters and what accounts for this? So a really great way, again, to introduce computational modeling, to take a look at the real, to make our physics equations more real, and then do an experiment to see how they test out. But JJ, there's more, isn't there?
Yeah, there is more. So another application or example that I like to use is a simple pendulum. Okay, and so
does anybody teach pendulums? Is that a physics concept that we teach?
Absolutely, yeah.
So we use them often, don't we?
Yeah, simple harmonic motion pendulums and simple harmonic motion are definitely a staple in the physics classroom, right? But a lot of times we want our students to understand the idea of period. When this thing swings back and forth, there's some period, and we say, hey, you can figure out if I can do that. No. So let me swap that back. Let me do this. You want me to play this PowerPoint? Can you see it now? So the pendulum, we want students to be able to calculate what the period of a pendulum is based on the length of the arm here, right? This is what's called the simple pendulum. The amount of mass that we add here doesn't actually affect the period, but we oftentimes just give students this relationship, right? Because there is calculus that's needed to help solve it. And not only that, but the calculus gets even more complex because we make what's called the small angle approximation. When we make the small angle approximation, it makes the calculus a little bit easier. But that's only assuming our pendulum swings like this far, right?
Oh, right. We haven't introduced a large variation.
Yeah, as soon as you swing it from this far, all of a sudden our period calculation gets thrown out the window. Okay, now this is where the power of computational modeling can really help us here. And again, the same thing we did for the projectile, we can do it for our pendulum, except instead of focusing on forces, since this thing's rotating, we're going to focus on torques. Okay?
Oh, great, okay.
And so if we know what the sum of the torque is on this thing, we know what the rotational impulses are, right? If we know what the rotational impulses are, we know what the change in angular momentum is. If we know what the change in angular momentum is, then we can figure out what the angular velocity is. If we know angular velocity, then we can figure out the changes in angular position. And that's exactly what
following that same line of logic, you start with what you know at the top and then do the minute calculations all the way down through to the bottom. And so that's what the power of the computer does, but that's also what the power of the Blockly in Capstone does, because I'm able to do that calculation. I can insert those numbers and start getting something out of it that makes sense.
Yeah, and so I'm going to do that, and then I'm going to swap over to here, and we can see the Capstone screen.
Got the Capstone screen, good.
And so I'm going to bring up my code again, and this looks a lot simpler than the last set of code, and the only reason it looks simpler is because we're not calculating x and y. We're just calculating theta, right? So if we know, again, we know what the torques are, then we know what the impulses are, then we know what the momentum changes are, then we know what the velocity changes are, then we know what the angular changes are. And so that's exactly what we have here. Here's our sum of the torques, right?
Sum of the torques.
Yeah.
I saw that movie.
And then here's the change in angular momentum, change in angular velocity, and then change in angular position. And so given that, we can simply just click that execute button there, and we get this ideal set of data. And
that's awesome.
Actually,
so
you know what I want to do first, though? I want to make sure this matches. Our length is 30, 100. Yep, it's perfect. Okay. So let me do that again. So we can create a set of model data.
So this is telling me, predictive, what this should perform as.
That's exactly right.
And you've included some variables in there to take into account the reality
Well, so this is just regular old pendulum, right?
Oh, okay.
But if we wanted to, we could redo the code to include a drag, the exact same drag that we
and
did
then
before.
see if that predictive model changed it at all.
That's
but
exactly
even
right.
so, I'm still doing a predictive model based on the ideal calculation for pendulum motion.
Yes, and what's cool here is I have also in this code, and I have it sort of stashed out here, I have this other theta 2 that's out here. And so theta is the angle of this thing, right? And if we know how that angle changes with respect to time, we can plot theta versus time. And then we get this beautiful graph that's out here like this.
Right.
What I've done here is I have created an expression, and I'm not going to go into a lot of detail about that, of what this, the equation of motion is for this pendulum when we do use the small angle approximation. So we say, I'm just going to throw that in
Just dropping
there.
that right in.
Yeah, and then it's disabled right now, but I can enable it by just doing that. And then I can do, I'm going to put this in here.
So you're modifying the code on the fly, by the way, just able to modify the code. And here we're introducing some additional reality where we're doing some approximations now.
Yeah, so what I'm going to do now is, let me see if I can add this. There it is. So now I've got code that's going to generate data for a pendulum that is using the small angle approximation, which we give our students all the time to make things more simple, and one that isn't, where we actually use the power of the computer to help us calculate the data, the real data.
Nice.
And it's for a release angle of 30 degrees. And so you see here, there's actually two sets of data overlapping on top of each other, right? And at first, they look like they're about the same value. Let me just make this a little bit bigger. But over time, you start to see them depart a little bit there.
Now
so
I'm seeing it. Yes.
the
now,
green and blue
now
are
I'm
starting to
seeing
separate.
Yep. Exactly.
And
so over time, the influence of that additional variable,
that simplification.
that
Yeah.
simplification of the calculation is beginning to show up in my data.
Yeah, and so we've got, and we can make it more dramatic by changing the angle that we start at. So the small angle approximation says, hey, you know, we can figure out this expression if we only have it go from here to here. But as soon as we get way out here, it's no good anymore. And this data shows that. You can see it start to separate like that. And if we wanted to, we could go a step further and we can actually collect real data, right? Does that turn on? It's on. And so let me connect.
So we're going to connect this wirelessly to the software.
Yep.
And we're going to compare. But the one thing I really like, JJ, is that I'm able to see that over a long period of time, a small calculation error can really turn into a disaster.
Oh yeah, yeah. And if you do an even larger release angle, it gets worse. It gets worse and worse and worse. So we've got that rotary motion sensor connected. We've got our theoretical data going on here in the bottom. Let me see if I can bring that run one up. There we go. And so I've got them pretty much lined up. One thing I'm going to do here is I'm going to turn off this code execution instead of having it draw new data. And so I'll click start, and then we're going to draw this up to about 30 degrees and then let it go. And we can see here the top graph is actual data being recorded by the sensor right now. And if we wanted to, we could measure the period. Oh, I locked that scale, that's okay. So we can take this coordinates tool and we can measure the period here. Just like that. There's the period value. 1.18 seconds, and we can do the same thing down
For
here.
the calculated.
Right. So in fact, let's try to get it right about in the same spot. Might not get it just exactly right. And so it's a 1.20.
So a very close calculation.
Yeah.
What was the real?
So the real was 1.18.
1.18,
Yeah.
and the calculated is 1.20.
Yeah.
So we can see that there are still some variables that might need to be accounted for. You might want to go back and adjust your model accordingly.
And that's exactly what I wanted to talk about next.
Wow.
This like you meant to do it.
That's incredible.
This is not actually an ideal simple pendulum because there is a rod here, a fixed rod that has mass, right? In a simple pendulum, we assume the arm has no mass. This has mass. So we could change our model to involve things like, a situation that is more representative of a physical pendulum, like this really is. And, or we could include things like drag in the pulley or rotational inertia of the pulley up here.
Which is accounting for that difference in the number that I'm seeing there. There are a whole bunch of things that need to be included to make this real.
Yeah, and then the last thing I want to show you is I've just taken a business card here, just like that, and put it on there. So now I've got this big cross-sectional area. So when this thing swings, now we've got air drag.
Air drag, a very large variable that needs to be added.
Yep.
And again, making this real for the students to see how to make a calculation real versus ideal.
That's right, and I have a file in here that I will provide for everybody that has this model built into it that includes air drag. So you could do something as simple as this.
You could do that, and you've already done it for them.
Yep, and this is it right here. And so now I've got this drag expression built in here, and it's included in the sum of the torques, and we have really done nothing vastly different than we just looked at. It's all about summing the forces. And in this case, since it's rotating, it's torques. So we take something very complex and we can simplify it and have the computer do all of the heavy work for us.
Additional stuff by taking in some reality, the drag, the mass, the angle, all of the things that we absolutely neglect when we're doing simple physics and say, hey, let's just pretend.
Yep.
But then when you take a look at the data, you see the pretending maybe isn't going to get you to Mars. You might actually miss Mars altogether, which is not what I want for my flight. So I would prefer the people that are doing the calculations for my Mars flight be doing computational modeling. And you can see how important it is.
Yeah, and the very last thing I promise, I even say, this is probably the third time I said last thing. The very last thing is that link that I promised you. So as I mentioned, I presented this as part of the AAPT Summer Meeting Conference. There's a link on this slide. It's a shortened link, bit.ly/PASCO AAPT SM 2021. And you can use that link to access a folder. It's a Google Drive folder that has all these files
that you've already put in there for them.
That's
so
correct.
you folks at home can go and do this right away with your students. If you're using Capstone, you've got students, you're advanced, and you want to engage them right away with the excitement of physics. Why is physics important? Because we can't get to Mars without it. Why is computational modeling important? Because if you don't use it, I'll end up on, Mercury? And who wants to live there?
And it's hot there.
And it's very hot there. So computational modeling is a very important aspect of what we do. Many of you have computer science standards, but even if you don't and you're just trying to look for ways to engage your kids are programming. They all love this opportunity to bring in real numbers in a coding canvas opportunity, and that's exactly what we're doing. Use what your kids enjoy, programming. Let them code, and while they're doing it, they're actually learning physics.
That's right.
That's great stuff. Well, thank you, JJ.
Thank you,
Really
JP.
appreciate that. And thank you, Heidi, for joining us today. And thank all of you. And as always, we wish you the best of luck, great teaching, and good day.